Hello everyone, this is Ashok, your personal guide and mentor. I welcome everyone to my YouTube channel AKB Tutorials. Here we are going to discuss and cover some important concepts of mechanical engineering that are very useful and helpful for competitive exam and job interviews. So let us start today's session.
So today we are going to learn one important topic of strength of material. That is, today's topic is elastic modulus. Now let us start with elastic modulus. So before going to elastic modulus, we will define what is called Hooke's law. So in basics we have studied what is Hooke's law. So Hooke's law is defined as within elastic limit the stress is directly proportional to strain. So this is given by within elastic limit the stress developed in a body is directly proportional to strain produced. Okay. So in a stress strain diagram, if we see within elastic limit, the curve is a straight line, and this is the sigma developed in a body and epsilon, that is strain developed in the body because of external load. So this is the body. The body is under external load P. Here P is a direct load. Because of this P, sigma developed in the body is given by P by A, that is resistance developed in the body by the original cross sectional area, and epsilon, that is strain developed in a body is given by, that is dl by L, where dl is the extension produced in the body over a length of L. Okay. So over a length of L, dl is the extension produced. So dl by L is equal to the strain developed in the body. So as per the Hooke's law, we can write sigma is directly proportional to epsilon, or we can write sigma is equal to some constant into epsilon. So here E is the elastic modulus. Now what is E? E is known as Young's modulus of elasticity. Young's modulus of elasticity. So what is Young's modulus of elasticity? E is given by sigma by epsilon, where sigma is known as direct stress because the stress produced because of the direct load. Direct load means it may be tensile load or compressive load. Because of direct load, the stress developed in the body is sigma and strain developed in the body is epsilon. So sigma by epsilon is known as Young's modulus of elasticity, and it is given by E. Now we will see the next, that is shear modulus of elasticity or modulus of rigidity. Shear modulus of elasticity. Shear modulus of elasticity, or is also known as modulus of rigidity or modulus of rigidity. So this is defined as and denoted by G. Modulus of rigidity is denoted by G, where G is equal to tau by say gamma, where tau is the shear stress developed in the body, shear stress developed in the body because of shear load, and gamma is equal to shear strain. So the ratio of shear stress to shear strain is called modulus of rigidity or shear modulus of elasticity. Now the next modulus, that is bulk modulus of elasticity. Bulk modulus of elasticity, and it is denoted by K. Bulk modulus of elasticity is denoted by K. Say a rectangular body, this is a three-dimensional body. This body is under uniform stress applied from all the directions. The uniform stress intensity applied over the body is, say here compressive stress we have considered. So uniform stress is acting over the body from all the directions, and because of this stress, because of this compressive load, some strain is developed in the body. Means the volume of the body will change. Change in volume is given by dV. Change in volume, and original volume of the body is equal to original volume, say is equal to V. So volumetric strain is given by volumetric strain. In this case, volumetric strain is given by change in volume, that is dV, to original volume. What is original volume? Volume is dV. So dV by V is the volumetric strain. So it is compressive strain because of the load is compressive load acting over the body. So volumetric strain is given by dV by V. Now bulk modulus of elasticity is defined as bulk modulus of elasticity K is equal to uniform stress intensity, say sigma by dV by V. So it is given negative sign because stress is negative. So minus sigma divided by dV by V is the volumetric strain. So it is denoted by epsilon V. So we have seen the three elastic constant, what is E, G and K. That is Young's modulus of elasticity owing stress and strain are direct stress and strain acting over the body. So that will produce, that is Young's modulus of elasticity. Then next, when shear stress is acting over the body, that is bulk modulus of elasticity, shear modulus of elasticity G, and G is given by tau by gamma, shear stress to shear strain, and K is the bulk modulus of elasticity, that is given by the ratio of uniform stress intensity to the volumetric strain. Now we will see that another elastic constant, that is called the Poissons ratio. Poissons ratio. So Poissons ratio, it is denoted by mu, and mu is given by, that is lateral strain to longitudinal strain. So we should learn what is lateral strain and longitudinal strain. Then it will be clear. That is, say a body of three-dimensional body. Say this is the three-dimensional body. The body is acting upon a unidirectional load P. P is the load acting over the body. So because of this direct load acting over the body, the deformation in the direction of load will take place. Say dl is the deformation over a length of L. Okay. So let's see the three dimensions of the body. Now, once the body elongates along the direction of load, so other directions, that is perpendicular to the load, it will decrease. Say the dimension L and this dimension is say W and this direction length is B. So L is the length, B is the width and W is the thickness of the body. L is W. Now in along direction L, dl is the increase in length because of direct load. P is acting along length L and along direction B. So there will be some change. Say dB is the change. So dB is the change, means it will reduce in size. Similarly, along direction W, change is dW. So this direction, the direction along the direction of the load is called longitudinal direction. Longitudinal direction. So there are other two directions, that is along the direction of W. So this is the direction L, this is the direction W, and this is the direction B. So whenever a load P is acting along length L, so L will increase and it will produce longitudinal strain in this direction, and it is given by, say, epsilon L is the longitudinal strain produced in the body, is given by dl by L. And in other two directions, perpendicular to L direction, that is B and W direction, the strain will be a compressive strain, and it is given by epsilon B is equal to dB by B, and epsilon W, that is along direction W, strain produced is given by dW by W. And this EB and EW are called lateral strain, and EL is called longitudinal strain. So these two, that is epsilon B and epsilon W, are equal. Okay. So within elastic limit, the ratio of lateral strain, either epsilon B or epsilon W, divided by the longitudinal strain, that is epsilon L, is known as Poissons ratio, and is given denoted by nu, that is epsilon B or epsilon W divided by epsilon L is called the Poissons ratio. Now we will see the relation between the elastic constants. So there are four elastic constants in strength of material, what we have seen. So that we will write elastic constant or elastic modulus, elastic constant or elastic modulus. there are 4 elastic constants, that is E, Young's modulus of elasticity. Second one is G, modulus of rigidity. Then third one is K, that is bulk modulus of elasticity. And fourth one is nu, that is Poissons ratio. So if we know any two of the elastic constant, any two elastic constant, then for a isotropic material the property can be defined properly or completely. So the properties of an isotropic body can be defined completely if we know any two of these properties. So now we'll see the relation between the elastic modulus or elastic constants, that is relation between elastic modulus so the first relation, that is relation between E and G, relation between E and G, that is Young's modulus of elasticity and modulus of rigidity. So there is a small proof given in every book, so you can directly write this and you have to remember this for solving the problem as well as for any competitive exam. These questions may come directly. So E is equal to 2G into 1 plus nu. So this is the relation between the Young's modulus of elasticity and modulus of rigidity, that is where E is equal to Young's modulus of elasticity, modulus of elasticity G is equal to modulus of rigidity and nu is the Poissons ratio. Okay, so if any two is known, then the third one can be easily obtained. So that's why for isotropic material the properties can be completely defined if any two modulus is known. Okay, next we will see the relation between E, K and G. E, K and G. E, K and G. So the relation between these three is given by, that is E is equal to 9 K G divided by 3K plus G. So this is the relation between E, K and G. So any two of these three are known, any two is known, then the third one can be easily obtained, where E is equal to Young's modulus of elasticity, K is equal to modulus of rigidity, bulk modulus of elasticity, and G is equal to modulus of rigidity. And next, the relation, that is relation between E and K. Relation between E and K. The third one is the relation between E and K can be written as E is equal to 3K into 1 minus 2 nu. where E is the Young modulus of elasticity, K is equal to the bulk modulus of elasticity, and mu is the Poissons ratio. So these are the relation between the elastic constant, and for isotropic material, two elastic constants are required to define the properties of the material completely. Now we'll see the volumetric strain. Volumetric strain. So, while defining bulk modulus, we have studied what is called volumetric strain. Is equal to change in volume to original volume. Now, how to find out this? So, we'll see now. First one, the case one, say a rectangular paralleloid. So for this, say a body, rectangular body is given, and the length of the body is L, width of the body is W, thickness is W, and width is B. So this is the body, this body is given. So original volume of the body, say VO is equal to original volume of the body, and it is given by L into B into W. So original volume of the body is given by L into B into W. So this is your VO. So by taking log from both sides, that is log VO is given by log L plus log B plus log W. Now deriving this or taking the derivation, so we can write dVO by VO is equal to dL by L plus dB by B plus dW by W. This is known as the volumetric strain. Change in volume. What is dVO? Because of the load acting over the body, change in volume is dVO over a volume of VO. So dVO to VO is the volumetric strain. So we can write this one as epsilon V is equal to dL by L, that is strain in L direction, epsilon L plus dB by B, that is strain in B direction, that is epsilon B, and dW by W, that is strain in W direction, epsilon W. So epsilon V, that is change in volume, is given by epsilon L plus epsilon B plus epsilon W. That is the sum of the strains produced in L direction, B direction, and W direction. Now we will see a cylindrical body. Say a cylindrical body of radius R, say radius is capital R, and the height of the cylinder is say H. H is the height of the cylinder. Now we can write V is the original volume of the body, that is original volume is given by pi r square into h. This is the volume of the body. So by taking log on both the sides, we can write log V is equal to log pi plus 2 log r plus log h. Now taking the derivation, so we can write or deriving this formula. So we can write dV by V is equal to derivation of a constant term. It will give 0 plus 2 dr by r plus dh by h. So dV by V is known as volumetric strain, is given by 2 into epsilon r, strain produced in r direction, plus dh by h, that is strain produced in h direction. So epsilon V, that is volumetric strain produced in a cylindrical body, is given by 2 into epsilon r, means strain produced in r direction, plus epsilon h, that is strain produced in h direction. Now we'll see if the body is a spherical body. So if the body is a spherical body, let a sphere of radius r. So this is a sphere of radius r, and the sphere is under uniform stress intensity. Now, what is the volume of the body? Volume of original volume is given by 4/3 pi into say r cube. So this is the volume of the body. Now taking log on both the sides, we can write log V is equal to log 4/3 pi plus log 3 log r. Now deriving this formula, we can write dV by V is equal to, this is a constant term, so if we take log of this term, it will give 0 plus 3 into dr by r. Now what is dV by V? It is epsilon V, that is volumetric strain produced in a spherical body, is given by 3 into epsilon r, that is radial strain. Okay. Now we'll see one more topic here that is not covered in the earlier videos, that is the stress strain diagram of a brittle body. So say a brittle body. So as per as the definition, what is a brittle body? The body which fails without much deformation. So that body is called a brittle body. So brittleness is the property, the body which is having brittleness property, that is called a brittle body, like cast iron. So without much deformation, the body fails. So if we see the stress strain diagram of this body, say cast iron, if we see the curve will be straight line for some distance, means up to proportional limit it will be straight line, then it will slightly bend and fail. So not much information is obtained from stress strain diagram. Even the upper limit means Young's modulus, that is upper yield point, is not clearly defined for this body, because without much deformation the body will fail. This is the failure point. Failure point, and this point is called the proportional limit. So up to proportional limit, the body, the curve is a straight line. Up to proportional limit, the curve is a straight line, and after that there will be very small deformation or no deformation at all, and the body will fail. So even that upper yield point is not clearly defined. For this, we are considering another term to define yield point. Okay, so that is called proof stress. Proof stress. So if we draw a line parallel to this straight line, okay, that is at 0.02% strain or deformation. 0.2% strain or deformation. So if we draw a parallel line to this straight line, so this point will define the sigma y value for this. Okay. So proof stress is the stress value at 0.02% of the deformation. Okay, this is all about this topic, and we will meet in the next video soon with some interesting topic. So be connected with us and give your valuable feedback so that we could improve our video. Thank you.
That's all for today's session. We would continue further on this topic in the next session. Keep being connected with us and ask any question in the comment section. Like, share, subscribe, and don't forget to press the bell icon to get notified for future videos. Thank you and see you soon.